Okay, so now this question is asking, tartaric acid is composed of carbon, hydrogen, and oxygen. CX, HX, and OX. Just a way of keeping track. A sample weighing 0.400 grams is subjected to combustion, okay, and produced that amount of carbon dioxide and that amount of water. So combustion is usually just when it reacts with oxygen gas and is being combusted, like burnt up in a sense, with energy to produce CO2 plus H2O. And that is what a combustion does. Now, it produced 0.469 grams of carbon dioxide and 0.144 grams of water. Okay? So these numbers will come into play right now. What we want to do is figure out, okay, based on this, we want to find the empirical formula of tartaric acid. Yes, we could just search it up, but for this question, and you can get sometimes unknown compounds, which is why it's important to just follow the steps here, so that way we can get it right. So, it said that it had 0.469 grams of carbon dioxide. We want to find out how many moles that is. So, 0.469 grams of CO2, okay, times how many grams per mole. So 1 mole turns out to be 44.009 grams of CO2. That is the molecular grams per mole. There we go. That is going to be the grams per mole for that. Okay, and with that, we find out that we only have 1.07 times 10 to the negative 2 moles of carbon dioxide. Okay, we also want to find out how much H2O we have. Okay, so with that, there's only 0.144 grams of H2O. And now the same thing, we multiply it. 1 mole of H2O is 18.015 grams. Okay, and now we've converted over to 0.80 times 10 to the negative 2 moles. Just making sure that I have that. And I just kept it like that because we're going to convert it anyways, because the goal here is that we want to actually find out specifically just how much carbon and how much hydrogen we have, because the oxygen we don't really know because it's used in here as well, but we do know that carbon and hydrogen are the only parts of that tartaric acid to translate over. So with that, actually, let's see, that would mean that if we take it one step further, let's use blue actually, for 1 mole of H2O there's 2 moles of H, okay, and per 1 mole of CO2 there's 1 mole of C. So this stays the same, 1.07 times 10 to the negative 2, but this one gets doubled, which is 1.60 times 10 to the negative 2 of C here and H correspondingly. Okay, so now we want to figure out the ratios, and once we figure out the ratio, we then in a sense multiply to get the nearest whole number. So we kind of divide each of them by themselves. So this is the amount of carbons, this is the amount of hydrogens. Okay, so now in a sense we go 1.07 divided by 1.07 to get the ratio of carbon, because it's a C, and because of that we get 1. And now for the hydrogen we go, because carbon is the lowest number, that's the number we have to use, we go 1.60 over 1.07. Okay, and with that, when I did that, I got around just making sure, I got around 1.5. So with that being known, that means that if we doubled everything, that'd be kind of to get the nearest whole number, because 1.5, we don't like that. So just multiply it times 2. Okay, so now we know the ratio is 2c for every 3h. Okay, so that is a success. And now that we have that, actually, okay, we can actually use that to find out how much oxygen was just in this part here. Because we know we have 4.400 grams, right? Okay, so if we then just make sure I'm doing this right, and because now we know the total grams of carbon that they could have possibly used for this scenario only. Okay, so that means that we convert it back to carbons, okay, but not carbons here, carbons over there. So we need, based on this, 1.07 moles of just carbon. Okay, now I have to multiply it. So the empirical formula for carbon, there's 1.07 times 10 to the negative 2. Can't forget that. Okay, and 12.011 grams of carbon per 1 mole, because this allows us to find specifically how much carbon was in our tartaric acid earlier. Okay, so we get, how much is that? 0.128 grams. So we can put that under here actually. So minus 0.128. That's to subtract the carbon, and now we're going to subtract the hydrogen as well to figure out how much oxygen there is, and then use that to find the moles. So now oxygen, okay, that is 1.60 times 10 to the negative 2. I mean, not oxygen, hydrogen. And we know from this it's only 1.008 grams per mole. So that also just translates to 0.016 grams. Okay, so we subtracted now the grams of oxygen, 0.016. Okay, so now this theoretically gives us our grams of oxygen in the tartaric acid. So with that, we know now that we have 0.256 grams of oxygen. Now let's convert that over to moles. Okay, 1 mole of oxygen is 15.999 grams. So with that, we were given, just to make sure, 1.60 times 10 to the negative 2 moles of oxygen. So now we have how many moles of oxygen there is, but this one also needs to go through the whole process of finding the ratios. So we also divide this by 1.07. We now get around 1.5. So we do the same, multiply by 2, because now we have, for every 2 carbons, there's 3 hydrogens and 3 oxygens. So that's what we've done for that question there. So with that, by breaking down that formula, we were actually able to solve the empirical formula, and we get C2H3O3. That's what we get there. Nice. And now they're asking for the actual molecular formula. They're saying that the molar mass of tartaric acid is 150 grams per mole. So you compare the grams per mole of this empirical formula with what they give you, and you can now guess the molecular formula. So with that, when you add up 2 carbons, 3 hydrogens, 3 oxygens, you get a total of 75.5 0.043 grams. And if it's saying it's 150 grams per mole, 150 divided by that, we're gonna get 2, meaning that this whole thing needs to be doubled to find its molecular formula. And now this is the molecular formula of tartaric acid, and this is the empirical. Okay, so with that, let's check. Yep, so they first found the mass of carbon. So we first found the moles, okay, and we translated that to the mass of carbon, which we subtracted from it. So that's good. And they also found the moles and mass of hydrogen, and then they used it to find the mass of oxygen right there, and then used to find the moles of each thing to find ratios, which is what we did. And then we got the empirical formula, and then when we got the molar mass, we saw that it was twice based on the grams per mole. So then we have to multiply everything by 2 and to get that molecular formula. So that's perfect. So this is correct. And now let's move on to question 8.